In 1963, a 13-year-old Tanzanian schoolboy named Erasto Mpemba noticed that his ice cream mix, when put into the freezer hot, froze faster than the cold mix from his classmate. He asked his physics teacher why. The physics teacher told him he was wrong. 6 years later, Mpemba and a visiting professor published a paper that physicists are still arguing about. Erasto Mpemba was a student at Magamba Secondary School in northeastern Tanzania, in the part of the country that grows up cold ice cream as a small after-school enterprise. The standard procedure was to mix milk and sugar, boil the mix, let it cool, and put it in a shared freezer. Mpemba, on the day in question, found a free spot in the freezer and put his mix in still hot. By the next morning, his ice cream had frozen and his classmates' started cooler had not. He asked his teacher. He was told he had imagined it. He asked again the next year. He was told the same thing. In 1966, the British physicist Denis Osborne, a visiting professor at the University College in Dar es Salaam, gave a lecture at Magamba. After the lecture, Mpemba asked him the question. Osborne replied that the observation was strange, took it seriously, and went back to his lab to test it. Mpemba's observation reproduced. In 1969, Mpemba and Osborne co-authored a paper in Physics Education, an institutional journal of the British Institute of Physics, formally describing the phenomenon as a real, reproducible effect. They named it after Mpemba. The phenomenon was not new in 1969. Aristotle described it in his Meteorologica in the 4th century before the Common Era, that water heated and then cooled freezes more quickly than water that has not been heated. Roger Bacon mentioned it in the 1300s. Francis Bacon and René Descartes both described variants of it in the 1600s. Modern physics had largely ignored these reports. The intuition that hot things take longer to cool than cold things is so foundational that the historical reports were generally treated as observational error. Mpemba's contribution was not to discover the effect. It was to bring it back into a peer-reviewed laboratory setting that demanded an explanation. No single mechanism is universally accepted by the physics community. Several candidate mechanisms have been proposed, and most working physicists believe the actual answer is some combination of them. Evaporation. Hot water loses mass through evaporation as it cools, so by the time it reaches freezing temperature, it has less water to freeze than the originally cold sample. Studies in sealed containers reduce but do not eliminate the effect. Convection. Hot water has stronger convective currents inside its container, distributing heat more efficiently to the surface where it can be lost. Cold water loses heat slowly because its convection is sluggish. Supercooling. Cold water can drop below freezing point without actually crystallizing if the system is undisturbed. Hot water, having gone through more vigorous thermal processes, may have fewer supercooling conducive conditions and crystallize more readily at zero. Dissolved gases. Hot water has lower dissolved gas content than cold water. Some published work argues that this difference affects nucleation behavior at the freezing point. Hydrogen bonding. A 2013 paper proposed that the hydrogen bonds in water molecules behave differently in initially hot samples, a controversial mechanism not universally accepted, but in the literature. The Mpemba effect has been hard to pin down because it does not always reproduce. Some experiments find it, some find a small effect, some find no effect at all. The difference between studies is usually traceable to the experimental setup, container shape, how full the container is, what the freezer's air circulation is doing, how the temperature is measured, whether the water is distilled or has dissolved minerals. A 2016 attempt at definitive replication by a group at the British National Physical Laboratory failed to find the effect under tightly controlled conditions and concluded that prior reports might have been artifacts. A subsequent body of work has argued that the National Physical Laboratory's protocol was atypical and missed the conditions under which the effect appears. The physics is not in serious dispute about whether thermodynamics works. The dispute is about whether there is a robust, reproducible regime in which an initially hotter sample reaches the freezing point first. In 2020, a group at Simon Fraser University in Canada published a paper in Nature showing the Mpemba effect in a colloidal system, not water, but a controlled set of microparticles in solution where temperature analogues could be precisely controlled and tracked. Their finding was that, in the colloidal system, an initially hotter sample could reach equilibrium faster than an initially cooler sample under specific conditions related to how far each sample is from equilibrium and what relaxation pathways are available. This is a system in which the underlying physics is much cleaner than water, and the observation was unambiguous. The 2020 paper does not prove that water exhibits the effect by the same mechanism. It does show that there is no thermodynamic principle preventing initially hot systems from reaching cold equilibrium faster than initially cool systems in some regimes. The Mpemba effect is, on this work, no longer a candidate for unphysical status. It is real in at least one system. Whether it is real in water remains contested. Erasto Mpemba completed his secondary education and went on to a career in the Tanzanian government's wildlife management sector. He has been interviewed about the effect periodically. He has consistently described the experience the way it happened, that he asked a question, that he was told he was wrong, and that a visiting physicist took him seriously. He has not made a career of the physics. The named effect is one of relatively few physics phenomena named after a 16-year-old. The story of how it got named carries some of its own weight in physics education circles. A schoolboy in Tanzania noticed something strange about ice cream. A visiting physicist took him seriously instead of correcting him. 60 years later, the question they wrote up is still in physics journals, partly because the underlying water chemistry is harder than anyone first thought, partly because a similar effect has now been demonstrated in cleaner systems where it cannot be dismissed. Aristotle wrote it down. Bacon wrote it down. Descartes wrote it down. Mpemba wrote it down. None of them was wrong about seeing it. The physics community, for most of the 20th century, was wrong to ignore it.